I love looking at data and processing data. We're looking at a one-third replica of the Sentinel-6 Freilich satellite. And there's multiple instruments on the satellite. We have the altimeter, we have the radiometer. My name is Shailen, Desai, and my role on the satellite is to combine the data from all of these different instruments that contribute to the measurement of sea surface height. The Earth's surface is covered by 70% oceans. We have millions of people, of course, living near coastlines. So the Sentinel-6 satellite is intended to take a snapshot of the state of the oceans, the hills and the valleys of the ocean surface around the globe. This antenna is sending a signal to the oceans, and that signal is bouncing back. When we combine the measurements from the last 30 years, this is the fourth of the series that I've been involved in. We're able to see how much has sea level changed over 30 years. I was born in Zimbabwe, moved to the United States, and came to college. I grew up in a country that was landlocked and had absolutely nothing to do with the oceans, and there I am helping to put together measurements of the oceans for the last 20 years. Because of that large surface area covered by the oceans, it influences climate and then affects the entire planet. For example, if there's an El Nino on the western coast of the Americas, is actually resulting in a drought in the country that I grew up in Zimbabwe. Wherever you live on this globe, the oceans will influence you in some form or the other.
Hi, I'm Raquel Villanueva with NASA's Jet Propulsion Laboratory in Southern California. You may know NASA best for exploring other planets, but we're also keeping a close eye on our own planet Earth. NASA is about to launch the US and European Sentinel-6 Freilich satellite. This satellite aims to collect the most accurate data yet on sea level and how it changes over time. JPL manages Sentinel-6 Freilich's mission for NASA. Shailen Desai is a measurement system engineer. He combines data from different instruments on the Sentinel-6 Freilich satellite. This data helps measure sea surface height. And he joins us live today to answer some of your questions. If you have any questions you'd like to ask, you can leave them right here in the comments or post them to social media with the hashtag Seeing the Seas. Thank you so much for joining us, Shailen.
Hi, Raquel.
Great, so let's get started. How does the Sentinel-6 Freilich satellite measure sea surface height?
So one way to think of this is think of someone that gave you an empty bucket and added some water to that bucket, and then challenged you to provide him with a measurement of the height of that water without actually getting wet. So one approach to doing this would be to measure the height of the top of the bucket from the outside of the bucket, and then to measure the height from the water to the top of the bucket from the inside of the bucket. Then when you difference those measurements, you end up with the height of the water with respect to the bottom of where the bucket is sitting. Similar to that bucket, we have the Sentinel-6 satellite, which is basically the top of the bucket, from which we measure the height of the satellite with respect to the center of the Earth. And then after that, we have instruments on the satellite that are measuring the height or the distance between the surface of the oceans with respect to the height of the satellite. When you difference those two measurements, that then provides you with a measurement of the sea surface height with respect to the center of the Earth. Then as the satellite is traveling around the Earth, in a circle around the Earth, at a speed of about 6 kilometers per second or almost 4 miles per second, the satellite is then taking these measurements of sea surface height directly beneath the satellite as it travels around the Earth. The satellite then goes around the Earth about 127 times in about 10 days, and essentially covers or takes measurements of the sea surface as the Earth is rotating beneath it, takes measurements of the sea surface height. And after 127 times around the Earth, it returns to the same location. The end result is that you end up with a snapshot of the global oceans every 10 days.
And then about that snapshot, how do the different instruments on the Sentinel-6 Freilich satellite contribute to this measurement?
So on the satellite, we have, for example, when you want to measure the top of the bucket with respect to the floor, the analogy to measure the height of the satellite, we have what we call tracking systems on the satellite. For example, a GPS receiver is one of the instruments that helps you provide the height and location of the satellite. The other instrument that is a tracking system as well is a French system called the Doris system. This is almost like a reverse GPS, where instead of receiving signals like GPS-like signals from GPS satellites, you're receiving signals from ground beacons on the surface of the Earth. And together, those two tracking systems then provide you an accurate measurement of where the satellite is or the height of the satellite with respect to the center of the Earth. Then we have the primary instrument on the satellite, which is called a radar altimeter. This instrument is sending a signal from the satellite to the surface of the oceans, and that signal is then bouncing off the surface of the oceans, reflecting back to the instrument, and the instrument is then measuring the time it takes for that signal to travel from the time it left the instrument to the time it returned. And because we know the speed of that signal, that measurement of time for the signal to bounce back then provides you a measure of the distance between the satellite and the sea surface. So given now our knowledge of the altitude of the satellite, so the top of the bucket, and the measurement of the distance between the satellite and the ocean surface, which is the measurement of inside the bucket, the difference in those two measurements then gives you a measurement of the sea surface height with respect to the center of the Earth. We also have an instrument on the satellite called a microwave radiometer, and this radiometer measures the water vapor content in the atmosphere. The problem with that radar altimeter signal as it is bouncing off the surface of the ocean is that it is delayed or slowed down by water vapor content in the atmosphere. And so by using the microwave radiometer to measure that water vapor content, we then know how much the signal has been slowed down by that water vapor. After we account for that, that radar signal then provides you a more accurate measurement of the distance between the sea surface and the satellite. So those are the main instruments that contribute to sea surface height.
And there's something in the video that you said about water that really stuck with me. You described the ocean as having hills and valleys. Can you elaborate more on what this means?
Sure. There are many contributions to the sea surface height that we observe from satellites. Each of these contributions can be thought of as layers on an onion. For example, as you peel the onion, from the largest layer of the onion, you start seeing the smaller and smaller layers and the smaller and smaller contributions to the observed sea surface height. The largest layer of the sea surface height onion, as you might like to think of it, is what we call the mean sea surface. So this mean sea surface is the average of the sea surface that you might take by taking measurements over a very long time, let's say over very many years. After you peel off that onion, and so after you know what that effect is, then you start seeing smaller effects. So another effect might be, for example, the effect of tides. Tides are caused by the gravitational pull of the sun and the moon. So, for example, if the moon is directly overhead, it'll pull on the water and cause a high on the water, so a hill, and nearby will then be the valleys. So this effect of tides comes from both the sun and the moon. After you take into account those effects of that layer of the sea surface height onion, then you can start seeing smaller effects. Like, as an example, you can see the effects of warmer and colder water. So, for example, if we think about that water in that bucket again, if you heated up that water, then that water would expand, and the water would then appear to be higher than what it was when it was at a cooler temperature. Similar to, for example, if you're in a swimming pool, you might find sometimes in a pool that there's different pockets of different temperatures of water. You might encounter a warmer pocket of water or a colder pocket of water. Well, the ocean is that big swimming pool where you also have warmer and colder pockets of water. And the warmer water, as I said, as you warm the water, it expands. So the warmer water is higher, and the cooler water is then lower. And those then again look like also contribute to these hills and valleys.
That is a great analogy. And now whenever I see an onion, I'm going to think of the sea. And can you tell us more about your career path that led you to JPL?
Sure. So I grew up in a small town in Zimbabwe, the third largest city in Zimbabwe, called Gweru. As I was growing up, I always enjoyed math and physics. I was fortunate enough that my parents took us on vacations that involved traveling on airplanes. And from those experiences, I became intrigued by airplanes, and my very first thought when I was younger was that I aspired to be a pilot. But on one of those vacations, we were lucky enough to visit the NASA Johnson Center in Houston. And from that experience, then I thought, oh, maybe I should become an astronaut. And so combining all of those experiences, after high school, I left Zimbabwe and attended college in the United States. I attended Purdue University, go Boilermakers. At Purdue, I pursued a degree in aeronautical and astronautical engineering. In one of those first classes at Purdue, the professor asked the class of about 150 how many wanted to be an astronaut, and about 90% or maybe all of the class raised their hands. In that instant in time, I realized that I needed to find something a little more unique as a career path, and so I kept looking at all of the different classes that I was experiencing at Purdue, and I came across a class that was teaching satellite navigation, and I became very interested in that, and then decided to pursue a graduate degree at the University of Colorado in Boulder, go Buffs, and at at in those classes, I was, of course, studied satellite navigation, but I also came across a class that taught the study of the size and the shape of the Earth using satellites that orbit around the Earth. And from that experience, I thought, oh, I wanted to perform research in that field, and I came across an opportunity to study the ocean tides using sea surface height measurements from the very first of the series of 4 satellites that precede the Sentinel-6 Michael Freilich satellite. And that satellite was called the Tobruk Poseidon satellite. So I did perform that research on ocean tides using the Tobruk Poseidon sea surface height measurements. And given my background in satellite navigation, I ended up landing a job at JPL, working as a navigation engineer, optical navigation engineer for the Deep Space One satellite. And about 2 years into JPL, I then landed a job. Again, given my experience with the Tobruk Poseidon and sea surface height measurements, I landed a job as the measurement system engineer for the Jason-1 satellite. And Jason-1 is the second of the 4 satellites that precede Sentinel-6 Michael Freilich. And from that time on Jason-1 as a measurement system engineer, I also became the measurement system engineer for Jason-2, Jason-3, and now Sentinel-6. And almost over 20 years have passed since that first experience with Jason-1.
Wow, that is a great story about following your own path and choosing to carve out a unique path of your own when you decide what you want to do in your career. So with that, is it okay if I start asking you some more social media questions that we have online?
Yeah, absolutely.
Great. One of them is from Elaine on Twitter, who kind of has a follow-up to your career path. She asked, some people have never seen an ocean or tide. What was it like growing up in a landlocked country? And did you ever think you'd be working on an ocean monitoring mission?
The short answer, I'll take the last question first. The short answer is I never envisioned working on an ocean observing mission. It's only when I was provided that first opportunity in graduate school to study ocean tides using the Tobruk Poseidon satellites that even came across my mind. Growing up in Zimbabwe, as you said, it's a landlocked country, so our experience with oceans, it was very limited, but of course we do have the Victoria Falls in Zimbabwe, so that's quite spectacular. But again, on some of those vacations that my parents took me on, we did visit some oceans. For example, we visited the Mozambique coast. We've also, on one of our vacations, traveled to Hawaii. And we've been to California as well. So I definitely had experience with the oceans. I definitely find the oceans as a calming influence, but certainly never thought I would be contributing to measuring the global oceans.
I actually do have the next question directly about the Sentinel-6 microfreilich. Since it's set to gather data on 90% of the ocean, Natalie on Twitter asks, what about the other 10%?
Yeah, so the Sentinel-6 satellite, the orbit of the satellite, or the path that it travels around the Earth, is inclined about 67 degrees from the equator. This means that all of the measurements are limited to the latitudes between 67 degrees south and 67 degrees north. And so we are unable to observe, at least not with the Sentinel-6 microfreilich satellite, we're not able to observe the oceans, which are the remaining oceans, which are primarily north of 67 degrees north latitude. So from 67 degrees north to 90 degrees north, we are unable to view those. And a large fraction of that is, of course, ice covered. So with this particular satellite, it's challenging to observe that. However, NASA does have a mission called ISAT-2, which is helping to measure ice sheet or ice cover, and so we can use one of those missions as well to observe ice in those northern latitudes.
So all work together. Now, speaking of your history too, that you touched on in an earlier question, Lewis on YouTube asks, is this the first joint NASA ESA mission, do you know?
This is certainly not the first joint NASA ESA mission. I believe NASA and ESA have collaborated on other NASA missions, but at least on this Sentinel, this heritage that Sentinel-6 microfreilich is built upon, we've had European partnerships between the U.S. and Europe since Topex Poseidon. Topex Poseidon was a collaboration between the French-based agency CNES and NASA. And the follow-on, Jason-1, was also between CNES and NASA. Jason-2 then introduced new partners. In addition to NASA and the French-based agency, we introduced NOAA, which is a U.S. NOAA is an atmospheric administration here in the U.S. And we have the European version of that, which is called EUMETSAT. And those four partners then worked on Jason-2 and Jason-3. And then Sentinel-6 microfreilich is, at least on this series, Sentinel-6 microfreilich is then the first of which ESA then joined those collaborations.
It's a real international collaboration there.
Absolutely, that's actually one of the probably the most fun part of working on these missions is those collaborations, because it brings in these diverse perspectives on how to investigate and look at these data, because they are quite different, but you certainly you'd appreciate different perspectives on looking at this information, and you build relationships. One of the people from the French-based agency, I've been working with him for over 20 years on all of these missions, and we're also working on a future mission as well.
I think our next question is a perfect segue from that. Linda on Facebook asks, do you think our knowledge of the sea is ever changing? And how do we update this knowledge? Is there a central sea database?
So these data that we collect from all of these missions are certainly collected by different agencies and assembled in, I would say, more user-friendly forms. For example, you can get grids of these 10-day snapshots of sea surface height measured by these satellites. These are the public is able to get these data sets. There are, of course, we have tide gauges around the Earth, which are individual instruments measuring sea surface height at individual spots. There are also places where we can pick up those data. In fact, we use those tide gauge measurements to help to determine or validate the accuracy of the measurements coming from the satellites. So there are certainly databases of all of these sea surface heights available in different forms. You might have to repeat the first question for me.
Of course. She wants to know if the knowledge of sea is ever changing.
Certainly, it's as I mentioned, that peeling the onion analogy is certainly appropriate here, because as the length of these measurements, the duration of these measurements increases, we're able to peel those layers of the onion to the smaller and smaller layers of that onion. As we learn about the top layers or the largest effects, and we learn how and we know how to model them or account for them, we are then able to then look at these as these smaller features or smaller amplitude features.
Now, Jeff on Facebook has a more technical question. What is the spatial resolution that will be attained with this new satellite?
So as I mentioned, most users of these measurements typically use, as I said, the path of the satellite is around the Earth and the ground speed of about 6 kilometers per second. Most users or scientific users will use the sea surface height measurements are averaged to the 1 second intervals along the satellite. So along the satellite ground track, you will basically, those users will use a sea surface height measurement that's about every 6 kilometers or every 3.7 miles along the ground track of the satellite. And I also mentioned the satellite takes about goes around the Earth about 127 times to cover the full Earth before coming to the same spot. So the resolution across track, so in longitude, let's say, is essentially 360 degrees divided by 254. Is the resolution then in that direction.
And then this is another question that kind of complements one we had earlier. Lewis on YouTube is asking, does this complement ISAT-2 in any way?
Certainly, as I described earlier, ISAT-2 is measuring ice, for example. The Sentinel-6 microfreilich is measuring the oceans, and all of this is tied to the Earth's water cycle, for example, right? So we have water from the ice sheets might be melting and providing adding content to the oceans, or for example, we might have water in rivers and lakes. There are then, if the rivers are flowing to the oceans, they're also contributing to the oceans, and then evaporation from the oceans has water going into the atmosphere, which then ends up coming back down as rain. So all of these missions are certainly interlinked. ISAT-2 is not the only one. NASA also has a mission called the GRACE mission, which is measuring mass, and that's also measuring water storage, is effectively water on the continents, water storage, and effectively as mass changes on the continent. So all of these satellites that NASA is contributing to are all interlinked in some way, understanding the Earth's water cycle, since water is, of course, so important to life and humanity.
And then Lewis on NASA Climate Facebook is asking, what level of precision does taking air moisture into account add? Are we talking centimeters or meters?
So the delay caused by the water vapor content in the atmosphere has a magnitude that ranges anywhere between 5 centimeters to up to 40 centimeters, but averaging probably, I think, in around the 10 to 20 centimeter range is the improvement you get by being able to measure that water vapor content.
Then we have another question. Talki on YouTube asks, how is this satellite going to help research about icebergs and rising water levels in the poles? And what makes this satellite unique from any others?
This satellite has some instruments that certainly have enhancements to some of the instruments. So there's certainly a long heritage of instrumentation that Sentinel-6 microfreilich builds upon. But some of the instruments have newer features. The receiver that's receiving GPS signals, for example, is also receiving signals from the European version of GPS, which is called Galileo. So it's tracking these different types of constellations. The radiometer also which is measuring the water vapor, has an instrument that helps improve the stability or the how much the error might change with time. So it's ensuring that error does not change with time. So because if that error does change with time, it might impact our understanding of sea level. The altimeter on the satellite is also quite enhanced in that it's expected to provide higher resolution of the sea surface height measurements and a higher accuracy of that measurement of the distance between the satellite and the sea surface.
And then we have time for two more questions. One is from Sarah P. on Facebook, who asks, can we see from the 30 years of data collection evidence of global warming?
That's, I think, a sensitive topic, probably better left to climate scientists. But I think from my perspective, I can tell you what the data tell us. The data, if you take the data from 30 years, we certainly have strong evidence that the observed sea surface height measurements are rising at about a level of about 3 millimeters per year. And the climate scientists will tell you that half of that is caused by ice melting from glaciers, for example, and the other half from ocean warming. So when I talk about that bucket, for example, if you added ice to that ice melting would then cause that water to rise. Or when you warm that water, it expands the water and also causes the height of the water to increase. So the
And I
data
think
certainly
you'll
support sea level rising, and the climate scientists are left then to explain the source of that.
Great. And I think you'll be the perfect person to answer this question from Sarah on Facebook, who asks, I'm a high school teacher in Nebraska. My students have a hard time relating our oceans and issues regarding climate change. What's the most important piece of data or research you've seen that really solidified the importance of this research for you?
Of course, seeing the average of the sea level rising over 30 years is quite important. But the El Nino event, for example, there's a 96, I think, or 90, 96, 97 El Nino event, as I mentioned in the video we saw at the start of the show, which is El Nino event that caused a warming a significant warming of the oceans off the western coast of the Americas. And that El Nino event affected climate in such a way that in the country that I grew up in, that El Nino event ended up causing a drought in my home country. So these are the types of experiences I've seen that helps me see the strong relationship between the oceans and climate. I mean, the oceans cover 70% of the Earth, and so that is going to influence the climate that we experience all around the Earth, whether you're in a landlocked country or living near the oceans.
It's all related and it's all connected.
Absolutely.
Great. Now, that's all the time for questions we have, but thank you so much for joining us today, Shailen.
Oh, thank you for having me.
Now, the Sentinel-6 Michael Freilich satellite is a true international collaboration, like we mentioned. It is being jointly developed by the European Space Agency, NASA, the European Organization for the Exploitation of Meteorological Satellites, and the National Oceanic and Atmospheric Administration, with funding support from the European Commission and technical support from the French space agency CNES. The Sentinel-6 Michael Freilich satellite is scheduled to launch on November 10th. For the latest on the mission, follow at NASA Earth on Twitter, Facebook, and Instagram. And you can watch all of the behind the spacecraft video profiles on the NASA 360 YouTube channel. We'll be doing live Q&As with Sentinel-6 Michael Freilich satellite team members each Wednesday afternoon. Follow and subscribe for those notifications. And at gotta get this right here, at NASA Earth Science, your home is our mission. Thanks for watching.